Hello everyone. What I'd like to do in this video is a similar exercise that we did in the last section in 3.4. We're going to go ahead, I think it was, maybe it wasn't 3.4, maybe it was at the end of 3.3 where we built polynomials with specific roots. That's what we're going to do here, except we're going to have a little bit of a complex number flavor in these type of problems. Okay, so let's just do a couple examples. So what we want to do, kind of the directions, is we're going to build a polynomial with we're going to say integer coefficients that satisfy the following. The following conditions. Okay. So if you don't remember what an integer is a whole number. So the integers, sometimes there's this kind of, it's called a blackboard font Z. So this blackboard font Z represents the set of integers. So what are integers? Integers are all the whole numbers. So 1, 2, 3, 4, and so on and so forth. And they're negatives. So for all these polynomials that we're going to build, I want the coefficients to be integers. So that means I can't have the coefficients be a fraction. I can't have the coefficients have square roots in them. The coefficients have to be of integer. Have to be integer values. So that's what it means that the polynomial has to have integer coefficients, and these are what the integers are. Okay, our first example. What are the conditions? What are the conditions? Okay, so they have to have integer coefficients. So we're always going to have that for these problems. We want integer coefficients. Okay, so for our first one, okay, integer coefficients, let's say degree 3, and has roots. It has roots. How about 1/2? 1/2 and 1 plus I. And 1 plus I. So these are our conditions, and we want to build a polynomial with these conditions. Okay, first thing I want to notice here is that it says that it's a degree 3 polynomial. So what does the fundamental theorem of algebra tell us about a third degree polynomial? A third degree polynomial has to have 3 roots. So notice here that it actually only gave me 2 of the roots. It only gave me 2 of them. But we have to remember something. If I have a polynomial and it has a complex number as one of its roots, what tags along? Remember that its conjugate tags along. So just with this information, I already know what the other root would be. So if 1 plus I is a root, 1 minus I is also a root. The complex roots come in conjugate pairs. Okay, so let's factor this. Okay, so if it has x equals, so if 1/2 is a root, that means I'll have an x minus 1/2. Okay, and I have 1 plus I and 1 minus I as a root, so I'll have a x minus a 1 plus I. And an x minus a 1 minus I. Again, oftentimes the book likes the negatives to be distributed. So x minus 1/2 times an x minus 1 minus I times x minus 1 plus I when I distribute in those minus signs. Okay. So what is wrong? What is wrong here? Notice that this will not have integer coefficients. Notice here that if I were to expand this, all of these x's are going to be hitting this 1/2. That's a problem. I'm going to get fractions. When I expand this. So what I need to make sure is that I don't have a fraction here. How can I fix that? Well, to keep these as roots, remember I could scale this polynomial by whatever I'd like. And let's say if I scale this polynomial by, say, I don't know, I think by 2, If I multiply this by 2, what's that going to do? If I distribute that 2 into here, what we're going to get is a 2x. 2 times 1/2 is a 1. I'll get 2x minus 1 times x minus 1 minus I times x minus 1 plus I. So I'm claiming that this is the polynomial that our boss wants. Okay. So notice when all the numbers do get multiplied, the first thing to notice is that I'm not going to get any fractions. Now you might be a little bit skeptical that when I multiply these out, that maybe I don't get integer coefficients. Are there going to be complex numbers? I claim that there won't be. And I'll show you why there won't be, and it's because these complex roots came in conjugate pairs. So when I multiply them out, I'll show you in a second that it's going to give us, we're going to get real numbers. Okay, so let me show you. So I'm going to erase just a little bit of this here. Okay. Okay. So I'm still going to keep the 2x minus 1. Okay, I'm just going to go ahead and take a deeper look at this piece right here. And I'm going to group them in a certain way. What I mean is, actually I'm going to write this. Let's write this as, how about I write this as x minus 1. I'm going to group these together. How about minus an I? Okay, how about I do this? Times. Okay, what am I going to get? I'm also going to write this as an x minus 1, an x minus 1, an x minus 1, plus I. Okay? So notice for a second if I were to expand these. Notice that this is kind of like that difference of squares pattern. If I were to FOIL this out, I get x minus 1 times x minus 1. So I'm going to get an x minus 1 quantity squared. I'm then going to get a plus an I times x minus 1. And I'm going to get a minus I times an x minus 1 from the O and the I in FOIL. But then I'm going to get a minus. I'm going to get a minus in I squared. So notice that these cancel out. So what I'm left with is x minus 1 squared. This is I squared. I squared is -1, so this is minus a -1. So putting this all together, I have my 2x minus 1 times, what is this going to be? This is going to be an x minus 1 quantity squared plus 1. So you can go ahead and continue expanding this if you'd like. How about I write this as x plus 2x minus 1 times, let's see, what if I expand that? I'm going to get an x squared minus a 2x plus a 1 when I expand this piece, plus an extra 1. So I get a 2x minus 1 times an x squared minus 2x plus 2, 2x. Now, you can go ahead and continue expanding this, but if I multiply all these out, I'm going to get a third-degree polynomial, and notice that all the coefficients would be integers. So that's actually one reason. If I do have a polynomial with integer coefficients, it has to have, if it has a complex root, it has to have its conjugate. It has to have its conjugate as a complex root, so that when it expands, all the imaginary numbers will cancel out, and I'll be left with something with just real coefficients. So this here is the answer to the problem. Okay, let's do another example. Okay. Let's see. So we have another polynomial. We're still going to want to have integer coefficients. We're still going to want integer coefficients. We're going to have the polynomial has a degree 5. It has, let's say it has 1/3 as a root. Let's say it has -1 as a root. Let's say it has -I as a root. Okay? let's say that this root here, -1, let's say that this has a multiplicity. Let's say this has a multiplicity of 2. And let's say we want a leading coefficient. Let's say we want a leading coefficient, let's say 9. Okay, so let's see what we're going to get here. Okay, so let's just start writing down the roots. Okay, so first of all, what I would like to do here is I have 1/3 as a root. Now there's two ways I can make that as a root. That either means that this polynomial has a factor of x minus 1/3, x minus 1/3, but the problem is that I want integer coefficients, so instead of having this polynomial have a linear factor of x minus 1/3, how about I change this and I say one of its linear factors will be, how about 3x minus 1? This linear factor will still have 1/3 as a root. Okay, what else will be true? Well, -1 is a root with multiplicity 2, so that means that x plus 1 is a factor, and it has a multiplicity of 2. Similarly, I also have that I is a root, or -I is a root, so x plus I is a root. But remember, if I have to have integer coefficients, if I have -I as a root, its complex conjugate's got to come along for the ride. So if -I is a root, I know that I is also a root. So x plus I and x minus I. Okay? So notice here that this had to be true for us to get an integer coefficient. I had to make sure to have integer coefficients, but also notice I needed to have a degree 5 polynomial, so I needed 5 roots. 1, I count this one twice, so 1, 2, 3, 4, 5. I needed the complex conjugate. Okay, so notice here if I were to expand this, I would get x times x, I would get x squared, I would get minus ix, I would get plus ix, and I would get a minus I squared. So this is just going to be x squared. These will cancel out, and I'm going to get minus I'm going to get minus a -1. Remember, I squared is -1, so I'm going to get an x squared plus 1. So this polynomial would factor to a 3x minus 1 times an x plus 1. If I decided to expand this out, I could have x squared plus 1. Okay. And now let's pause ourselves and ask ourselves the question, what else did we need here? We needed a leading coefficient of 3. I'm sorry, a leading coefficient of 9. So, but when I look here, what's the leading coefficient of this polynomial? Well, if I were to multiply everything out, the leading coefficient will just come from me multiplying the first term and all these factors here together. So the leading term here will be a 3x times an x, a 3x squared, a 3x squared times an x squared. Right now, oh, this has a multiplicity of 2. Sorry, this is a multiplicity of 2. So I'm going to get an x squared here, so x squared times 3x, I'll get 3x cubed times an x squared. So I'm going to get a 3x to the 5th as my leading term. My leading coefficient is 3. I want the leading coefficient to be 9, so I can scale this polynomial by whatever I want, and it won't affect the roots. So how do I make a 3 to 9? I'm going to hit it with a 3. So here we have the polynomial p of x. This would be our answer. Now, I would accept this as an answer if you actually wanted to go ahead and multiply together the factors that have the complex roots. Okay. But if you wrote this as your answer, I would still accept this with full credit. So that's how we build polynomials with specific degrees, making sure they have integer coefficients. And for these type of problems, we have to remember a little bit about the fundamental theorem of algebra. An nth degree polynomial has n roots, counting multiplicity. Some of them can be complex. If they have integer coefficients, if I get one complex root, its complex conjugate must also be a root. Okay, that's it for 3.5. We'll see you in the next video. Take care.